Okay, today we will take up our topic functions and binary operation. Later on we will take binary operations. So functions we have already studied in class 11th, and I will take a quick summary of the things pertaining to functions read there in class 11. So first and foremost we come to the definition of function. So the definition of function there has been defined in terms of relation. So function basically is a special relation, say from set A to set B, such that each element of set A has one and only one image in the set B. Now, if we constitute this relation set as we have seen earlier, then this essentially consists of doublets, where the first element will be from the set A and the second element will be from the set B, and the second element will is said to be the image under the relation of element A of the first set, that is the domain of the relation. Now, so we can write down the definition of function. That's a good one. Its definition is a relation is called a function. A relation is called a function if and relation will be from one set to another. A relation from set A to set B, from set A to set B is called a function if each element of A has one and only one image in B. So two things are necessary: that all the elements of your set A should have an image. And the second thing which is important here, if at all the relation has to be a function, is that only one image should be for each element of your set A, that which is the domain of the function. Now do remember here, see, that in the relation set, you call the, if the relation set, you know that it essentially consists of doublets. And in doublets, the second element is said to be the image of the first element. Second element belongs to your codomain of your relation, and this first element belongs to the set A, which is the domain of your relation. Now, symbolically, how we make use of it. See, this function is denoted as f, two dots followed by two dots, A to B. If a function is from A to B, then it is symbolically written as in this manner. So symbolic representation of function. Representation of function is given like this. Now another important thing, that if we write that the element B, small b, is the image of the element small a in the in this thing, relation. Then that is to say, if in the relation set R, suppose A1, B1 is some element and say A2, B2 are, suppose only two elements are there, then see, you say that the second element is the image of first element. And symbolically, this fact is represented as FA1 is equal to B1. It is better said to be that the image of A1 element is B1, or functional value of A1 element is B1, where A1 will be the element of capital A set and B1 will be the element of capital B set. So this is the symbolic notation of showing the image. So this is what? Symbolic notation of saying that image of that image or say functional value of A1 belonging to A is B1 belonging to B. So please do remember these two representations. This is for function and this is for denoting that the image of a particular element, say A1 of domain, is B1. B1 will of course be belonging to your set to codomain. Now this is all about the symbolic representation of function. Now once again I am visiting this definition here, because this definition needs to be understood in the correct perspective. So two things which are essential here is that each element of your domain, each element, no element should be left out whose image is not present in the codomain. So one is this each element of domain, and the second characteristic should be that none of the elements here should have more than one image, Now pictorially, see, I will explain this definition, which of course will further help you in understanding this concept of function in a better manner. So suppose A is some set. I am showing now, see, the pictorial representation of the definition, pictorial representation of the definition, representation of function. So see what should happen. A is set, B is another set, and say it consists of element A1, A2, A3, A4. And this consists of say B1, B2, B3, B4, B5. 5 elements here. Now see, suppose A1 goes to B1, A2 goes to B5, A3 goes to B1, and A4 goes to say B3. Now see, this is example of function because each element is having image. Each image of FA1 is what? B1. Image of A2 is what? It is B5. Image of A3 is what? It is again B1. And what is the image of A4? Again B3. So what we are noticing is that each element is having the image. Each element of the domain set is having the image. And moreover, none of the element here is having more than one images. See, all the elements in the domain are having only one images. So this is what the requirement is. But now see, so this is function. This is function. This pictorial representation is that of function. But if suppose the case would have been like this, that suppose A4 or say A2, one image is A2 here and another image is like again B2. Similarly, A1 is imaging B1 or A1 is having image B5 as well. Then see, this will not be a function. This will not be a function for the simple reason that FA1 is equal to B1 and FA1 is equal to B5. So A1 is having two images. A1 element is having two images, and that's the reason that this particular association will not be called a function, because if at all it is to be a function, then each element here not only A1 but even this element here, A2 is also having two images. But even if one of the element is having two or more than two images, then it see, and rest all are having one images, then also it won't be a function. And then another example would be like if some element is left out. For example, suppose I take one example and I say its element are 0, 10, theta. And here it is number 7, shape, and say say ship and Rita. And chair suppose is going to Rita, the element pen is going to say 7, and that's the representation. So it won't be a function. It won't be a function because theta is not having any image in this thing. So if theta is again say having image like this, then now it will be a function. So see, only two things you have to check in. That each element here should have a image in the set B or association in the set B, and these images or association should be unique. Unique means one and only one. Means it can't be the case that any element in the domain is having more than one images. If that is the case, then see, it won't be a function. So these two things you have to take in care as far as this definition of function is concerned. Now, what else you have read in class 11 was the graph of certain important functions. So see, like a modulus function, signum function, greatest integer function, fx is equal to say x square, and many others. And see, shortly you will be studying the trigonometric functions also, their graphs, the inverse trigonometric function graph here in class 12, so in the next chapter. So now here I will take some important graphs. First graph will be of the say modulus function, which we will be using it. Modulus function is defined like fx is equal to x if x is greater than 0 or equal to 0, and this is equal to minus x if x is less than 0, because see, you can write like this, because fx is equal to, after all it is mod x. Mod x, it can be rewritten like this. So fx is equal to x when x is greater than equal to 0. So it means it will be a line 45 degrees like this. Making y is equal to mx plus c. M here is 1 and c is 0, so it will pass through the origin and it will make 45 degrees. And then minus 1. So minus 1 means what? Please see to it. It will be like 180 minus 45. So again here on the left side, see that will be like this, and this angle will be 45 degrees. So because 180 minus 45, 10, if you take it little, then it will be minus 1. Here the slope is minus 1. So it will be making 45 degrees. So this is the graph of modulus function. And for signum function, which is defined like fx is equal to 1 if x is greater than 0 is equal to 0 if x is equal to 0 and is equal to minus 1 if x is less than 0. Then see, it's simple. Its graph on the left side will be what? Like this thing, it is minus 1 mark. This is say plus 1 mark, this is 0 here. So this point of course C will be 0 because at 0 the value is 0 and here see again see it will be a constant function here. This line you will ignore. So at 0 it is 0, then see for all these negative numbers it is. So this is the graph of the signum function. And then see we will take the graph of say greatest integer function. It's again an important graph here. And greatest integer function, you have read it, but still we will take it because we will be using it frequently. Greatest integer function, it is written as fx is equal to like this and it is equal to nothing but greatest integer less than equal to x. That's all. So now see how to find it out. If it is 0, of course, now consider the interval 0 to 1. 0 to 1. Open interval. So what the thing will be? Here, for this, if x is anything here, then what is this thing? For any this thing, 0 would be the value. 0 would be the value in this entire interval which is closed on the left hand side and open on this thing. So here at 0 it is 0 and throughout here see it will be 1. Now suppose this is the mark 1, this is the mark 2, then see for 1 to 2, exactly at 2 it will be 2, but in this interval, in this which is closed on the left side, the value will always be 1. You take x, any element in this interval. And the greatest integer function will be what here? It will be 1. Because it will be here in this interval. 1, see, it is slightly away because this is much of, this is 1. And this is 2. This is 2. This is the mark 3. And so on. So 0 to 1, of course, see, it is like this for all the, this thing, for this interval, it is this thing. At 1, it will be exactly 1. So 1 to 2 it will be like this and 2 it will be what? So you will round it up and at 2 it will be like this, 2 to 3 it will go like this, at 3 it will be almost this way, so this way. And 0 to 1 it is this thing and at exactly 1 it will be 1. Similarly for interval minus 1 to 0, minus 1 on this thing 0. Open on this side, the value will be minus 1. So minus 1 here, so here see this is say minus 1 here, so it will be like this, it will be like this and exactly at this thing, this is how much? Minus 1, so it is here at 0 see, the value will become 0, so this one you will skip and it is like this thing, between minus 1 and minus 2. Minus 2 to, because see here at 0 the value will be 0. Minus 2 close on this thing, minus 1. What the value will be? Minus 2 only. So it is minus 2 mark suppose is here. So the value between this minus 2 close on the left, open on this thing will be minus 2. And exactly at minus 1, see it will be minus 1. So this is how the graph of greatest integer is obtained. So these are the important graphs. Then see one more thing here which you read in your class 11 was the real this thing, real valued function and real function. So let us understand the difference between the two. Real valued function, okay, and real functions. See, the difference is that in real valued functions, this codomain is a subset of your real numbers. that is the functional value, their images will be real numbers. So here the codomain in real valued function, yes, the codomain is a subset of R. Whereas in real functions, both the domain and codomain, both of them are subsets of this real sets. So in real functions, both domain and codomain, are functions, are subsets of real numbers, entire real line. So it is a subset of this thing. So this is what we need to understand, this difference. And then see, we read about this algebra of real functions. So therein see if f1 was a real function from R1 to R2, and say f2 is a function from say R1 to say R3, then f1 plus f2 function was defined like f1 plus f2 function x here was nothing but f1x plus f2x here. So point is that you from given to real functions having common domain. See here the domain is common, they are real values, they are subset, but here they can acquire different values. So this is how you define. Then you define f1, f2 function. So f1, f2x likewise you have obtained to be what? f1x into f2x, and then you read about kfx function means a scalar multiple of this of a given function, where k is some non-zero real number. So it was nothing but k f1x, and then see you the f1 upon f2 function you read. So f1 f2x was nothing but f1x upon f2x, provided f2x is not equal to 0 throughout the domain, where x is the element of your domain D, that is R. Because so remember that when these two, so this was all the algebra of real functions which you read in class 11th. So now we proceed further, and we will take up the things which we have to study in class 11th as far as functions are concerned. And here mainly we will study different types of functions. So this is what we will take it up right now. So types of functions. That is from where our syllabus of class 12 is begins. So types of functions. Okay. Now, first and foremost, we will study here one function and manual function. So first function which we will study here is injective function. Injective, or it is known as one-one function also. One-one function. Injective of one-one function. So now it's very simple. A function is said to be injective or one-one, provided each element of the domain has distinct image. Means all the images of all the elements of the domain are different. No two elements should have the same image. So if such is a function, then you call it to be a injective function or one-one function. So write down, if the images of all the elements of domain, of all the elements of domain are different, are distinct, are different, then function is 1. Then function is 1, 1. Then function is 1, 1. Now see, same thing, you can also express it like, that is to say, see, mathematically that is to say, if fx1 is equal to fx2, fx1 is equal to fx2, this implies x1 is equal to x2 for every x1, x2 belonging to your set A. If f is a function, that is to say, if f is a function from A to B, and if f is a function and if fx1 is equal to fx2, this implies x1 is equal to x2 for every x1, x2 belonging to your set A, that is domain. See what it means. If x1 and x2 are having same images, then both these elements should also be same. Then only, see, if they are distinct, then what it will be implying is that two distinct elements of the domain are having the same image. So if that should not happen, because each element should have the distinct image, and that's why mathematically, see, whenever we have to show that the functions are 1, 1, then we will employ this particular criteria for proving the result as far as questions are concerned. That is, we will assume that if fx1 is equal to fx2, then we need to show that x1 will be equal to x2, where x1, x2 are any two elements of the domain. Now, if a function is not 1, 1, then what it is? Then, if a function is not 1, 1, then it will be many 1. So, many 1 is, so in many 1, what will essentially, what will the essential feature of this many 1? And there is, see, at least two elements of the domain will certainly have the same image, So at least two elements will certainly exist. There could be many more, but at least two elements will certainly have same image. Then the function is called many 1. If function is not 1, 1, then it ought to be many 1. Now, another type of function which we will be studying will be onto functions. We will be studying will be onto functions. Please see, onto functions. Now what it has to say? It simply says if f is a function from A to B, pictorially I will also show it to you. It is A, it is B, and f is a function from A to B. Then function is said to be onto if each element of the codomain, please remember, if each element of the codomain is the image of some element of the domain. Please see, what I wish to say is that you take any arbitrary element in the domain and see if all the elements, so not arbitrary, if you take any element here in, then it should have a pre-image in the domain. So please see, we explained you, if we are writing fa is equal to b, then we say that the image of a small a element of domain is b. Now, same thing, in terms of pre-image, we will say that the pre-image of b is small a, where b is the element of codomain and a is the element of domain. Now, in a function, it can well happen that the pre-image of any element of the domain could be 2, could be 3, could be even more than that. And there could be a case. Still, it will be a function. But vice versa is not true, because if at all it is a function, then its images in the codomain should be unique. So that aspect you also have to look into. So pre-image word when we are using, then there it will be simpler to define this thing, and this onto function this thing. There we can say that each element in the codomain should certainly have a pre-image in B. Pre-image in domain. So this is one definition. Or other definition is what all elements here should be the image of some element of that domain. So both ways, either you say number one, for defining the onto function, each element in codomain should have image of some element in domain. This is one definition. Now same thing you can say, see, all these things can be said in different manners, but essentially the meaning remains same. So second way is what? Each element of codomain should have a pre-image in domain. Now, if we will give you another definition here, and what that definition will be, okay, third definition we will be giving you in mathematical manner, and it will simply say for every B belonging to B, where B is your codomain, here you can write codomain because function you have taken to be from A to B, codomain. For every B belonging to it now, there exists an element A belonging to capital A such that FA is equal to B. This is how onto function has been defined differently, all having the same meaning. Now, if function is not onto, then what should happen? Then it is known as into function. If function is not onto, then what it should be? It is then into function. If function is not onto, then it is into function. Now, what I will write is into function. In into function, what actually will happen? If a function is not onto, then it is into. So first definition is, if f is not onto, then it is into. Okay. Second definition is that, see, at least one element will exist in codomain, which is not the image of any element of the domain. So if a function is from A to B, if f is a function from A to B, then it is into if there exists an element B0 belonging to B such that FA is not equal to B0 for every A belonging to capital A, then the function is said to be into. So broadly, these are the four divisions: 1, 1, where each elements of domain will have distinct images. Many one. If see any two elements of the domain are having same images, then the function is called many one. Then onto function. In onto function, what should happen? Each element of the codomain should have an image, should have a pre-image in the domain, should have a pre-image in the domain. Or in other words, see, if you take any element here in the codomain, that it should be the image of some element of the domain. So this is how you define this onto function. And for into function, what you need to prove is that there do exist one element here in the codomain of the function which is not the image of any element of the domain. So this is mathematically you would be writing like this, that if f is a function from a to b, then there exists an element b naught. Existence of one element will certainly be there, call it b naught, which will not be the image. See, fa is not equal to b naught for every a belonging to domain. So these are four basic classification of this functions: one function, many-one function, onto function, and into functions. Now, this onto functions are also known as surjective functions. Onto is also known as surjective functions. So another term for onto function is surjective functions. Surjective. Now, a very important term you will be coming across, and that is bijective function. A function is said to be bijective if it is 1, 1 and onto. If it is 1, 1 and onto. If a function, if f a to b is 1, 1, injective, 1, 1 means injective and onto, that is surjective. Then it is called, then f is, function is called bijective, is called bijective, is called bijective. So this is all about these different types of functions. Now here see, first I will explain you a few both these concepts of functions and this different types of functions. We will take one or two problems so that things become more clear to you. Okay, one problem I would like to discuss here is, first let me take a simple problem here, and that problem of course will be from your, okay, let me take it from your book straight away. Okay, but before I take this problem, I will tell you some good things here. Now see, suppose I take a function fx is equal to say root x, and both my function is from R to R, function is from my R to R, and fx is equal to say square root of x. Now see, I have to find it out whether the function defined in this particular manner over R to R, will it be a function or not? Now the answer is simple. Answer is simple. It is not a function. Why it is not a function? Because see, negative numbers will not have the images, one thing. Negative numbers will not have the images. The square root of a negative number is not a real number. We can prove it. We can prove it. So see, a square root of negative numbers, of negative real numbers is not real number. Is not real number. This you know it, but how to prove this result? Okay? If you want to prove it, see how we can prove it. Let us see it. Suppose it is a real number. Contradiction method. If it is a real number, then what it would be? If you take any negative number, then suppose the square root of that number, say the number is say -7 suppose. Say you call it x and say x is the real number. Then x will be positive or negative or 0. Now see if it is positive, then the square root of positive number is what? A positive number. The square of 0 is what? 0. So it will still be not -7. And the square of a negative number is what? Again positive. So in no way x will be a real number. Now comes here the definition here say of a square root. See, this is also very important to understand here what the definition of this square root, cube root, nth root that is. So a square root definition, of course, see, you can say a square root of a number x is a number y such that y square is equal to x. And see square root, if I write a square root of x. Don't write, if I write only a square root, of course, okay. A square root of x is a number y, so that y square. If I write cube root of x, what? It is a number, again y, such that y cube is equal to x. If somebody asks me what is the fourth root of x, of any number x, x is the real number, of course. It is a number, you say it is a number y, such that y raised to power 4 is equal to x. And you can generalize it. Nth root of a number x is a real number, of course. So say it is a number y, such that y raised to power n is equal to x. So this is how we define it. Now see, once this definition is there, then see, there is one thing. Okay. So first, essentially see, we have taken r to r plus. Now if suppose we take r, then see, the question is, will it be a function now? Now see, here one thing is there. Let us understand how we have defined our function. Function we have defined to be what? Root x. Now, here see, when we take the square root of a number, then we get two values. If we take cube root, we get 3 values. If we get nth roots of a number, we get n values. But see, these n values, will they be belonging to real set? So that is not there. These n values will be belonging into the complex set. Now among these n values, few of them will be belonging to real number set also, and others may be in the pure imaginary set. Now, point is, like if I here ask you, now I have restricted to r plus, so that this problem of not having the images of negative numbers, that gets rid of it. I have restricted I have changed my domain from r to r plus, and then I am finding that whether now it will be a function. So still people will say, yes, if I take 4 here, then the square root of 4 is what? Plus 2 and minus 2 both. Plus 2 and minus 2 both. So still it won't be a function, because it is giving you 2 images. So what we need to understand first of all is that, let us look into it. See, as I said, if you take a number, any number, and you take its nth root, you will be getting n values. Now, these values will be present in the complex set. They are few of them could be pure real numbers, but all these n values will be lying in the complex number set. But now, then see, if we take a square root, then of course we won't be getting it in the real also. See, we have seen that for 4 you are having 2 values. But then see, one important theorem which you need to know is, and that is regarding the principal nth root. Principal nth root. Nth root. Now it is could be square root, principal square root, principal cube root, principal nth root, whatever. Now what it has to say, if x is a real number, is a positive number, and you are calculating its nth root, and you are calculating its nth root, you will get x values, say x1, x2 and xn in the set of complex number. But then in these n values, there will be one value which will be positive real number, and that value is known as the principal nth root, and that value is known as the principal nth root, and we denote it by n root x. Otherwise, see, for nth root we denote like this, x raised to power 1 by n. See, this is the thing. So whenever we say square root of x like this, it means we are talking about the principal square root, and we have already this confined our domain to positive real number. So here, see, this negative value will be ignored. But if you would have been written like this, x raised to power 1 by 2, then it would have not been a function. It had not been function. Here, see, you have to consider principal square root, then it will be a function, because then the square root of 4 will be only 2. So remember that in order to make this one fx is equal to root x to be a function, you have to restrict your this domain to r plus, and then the principal nth root, square root, has to be taken. So then it will be a function. Now, here on 1-1, let us take few questions from your book. Okay, the first question is, let this is question 8 of your book. I am doing it. It is on 1-1 and this thing ontoness. So it says, let A and B be sets. Let A and B be sets. Let A and B be sets. And then you have to show that f is function from where to where? A cross B to B cross A. To B cross A and define such that how it is defined? The function is defined like this: f a b is equal to b a, because b a has got to be the element of b cross a, and a, where of course see, a is the element of a and b is the element of b. This is how you have defined, and you have to show that this function is a bijective function. This function is a bijective function. Okay, so if it is a bijective, then it ought to be 1-1, it ought to be onto. So for proving injectiveness, for proving injectiveness here, injectiveness of function, what we need to do? Let a1 b1 and a2 b2 be the element of a cross b such that f a1 b1 is equal to f a2 b2, and then if we can show that a1 b1 doublet is equal to a2 b2 doublet, then our assumption will be proved. So fa1 b1 is equal to a2 b2. fa1 b1 is defined in what manner? b1 a1, and so b1 a1 should be equal to b2 a2. Okay. Now 2 and tuples are equal when their corresponding elements are equal. These first are equal, second are equal, third is equal, and its position this element is equal to the element, position element in the second element tablet. So in doublets, first element will be equal, second. So this implies by equivalence of doublets, B1 will be equal to B2 and A1 will be equal to A2, implying that A1 B1 is equal to what? At in case of A1, what we can write? A2 and B2. So yep, this has been proved. The F A1 B1 is equal to Fa2 B2. This means that A1 B1 is equal to A2 B2. So injectiveness is proved. Let us prove the ontoness. Yes. For proving ontoness, what we need to do is that we will take any arbitrary element in the codomain. So let B0, A0 be the element of B cross A. So this implies so here B0 is the element of B, A0 is the element of A. Now this is an arbitrary element of the codomain, and we will show that there exists an element in the domain whose image is this element. We can show this thing that each element of the codomain is having some element here such that the image of that element of domain is the given number of codomain. Then it becomes a onto function. So B0 A0. Okay. Now B0 A0 is the element of BA. This implies A0 B0 is the element of A cross B, that is domain. Now if we take the image of A0 B0, then what it will be? It is nothing but B0 A0. And as such, we have shown that there do exist an element in the codomain whose image is B0 A0, and hence the function will be onto function. So this is how we have been able to establish the bisectiveness of this function given by FAB is equal to BA. Now next problem here, the ninth problem, okay, of your book here. Let me make it question 9. What it says, a function has been defined like this. F is a function from natural number to natural number, and defined by such that defined as yes, Fn is equal to, please see, Fn is equal to what? N plus 1 by 2 if n is odd. And is equal to n by 2 if n is even. You have to ensure that this function is, whether this function is bisective or not. Okay. So first let us see whether it is 1, 1 or not. So in 1, 1 there will be 3 cases. Either both x1 and x2 are even, either both of them are odd, or both of them are, or one of them is even and another is odd. So case 1, when both x1 and x2 are odd, then it's simple to show that the function will be 1, 1. Because then fx1 is equal to fx2 implies what? Fx1 will be what? X1 and x2 are odd, so x1 1 plus 1 by 2 is equal to x2 plus 1 by 2, implying that x1 is equal to x2. In case A implies injectiveness. That is, the function is 1, 1. Case 2, when both x1 and x2 are even, then fx1 is equal to fx2 implies x1 by 2 is equal to x2 by 2, implying that x1 is equal to x2. x1 is equal to x2. Again, so case B implies injectiveness, one-oneness or injectiveness, one-oneness. Okay. Now, third case we will consider, and we will see let x1 be even or x2 be even. Let x1 is equal to say even and x2 is equal to odd. Okay, then fx1 is equal to fx2. What does it imply? x1 is even means x1 by 2 is equal to x2 plus 1 by 2. So what does it mean? 2 to cancel. So x1, okay, minus x2 is equal to 1. So this is what we are getting it. Now, x1 is even number, x2 is odd. Okay, and we see that if you have taken some even number and you are looking at number, the odd number just before it, then the difference between an even number and odd number is always 1. So this will always hold good. For example, 8 you have taken. 8 is an even number. And just before it 7 you take it. 7 is the odd number. 8 minus 7 is what? 1. So the image of 8th element and that of 7th element, they will be same. They will be same. And elements are not same. And elements are not same because see, the image of, for example here, if you take x1 even, say 8, so what will be the image? It will be 4, and by 2. It will be 8 by 2, that is 4. And what will be the image of 7? 7 will be 7 plus 1 by 2, again 4. So both these elements, one even, one odd, they are having the same images. And but see, elements are different. x1 and x2 are different. One is 8, other is 7. So this is one example where this one-oneness will not be there, and hence the function will not be a one-one function. Because if at all it has to be one-one function, then this fx1 is, whenever fx1 is equal to fx2, this should imply that x1 should be equal to x2. All elements should have the different images. So with this, and so therefore we need not to check now onto next because the function is not one-one. And as such, it won't be a bijective function. It won't be a bijective function. Now, I will take binary operations here. The second topic, though it is not in the syllabus right now, but see, we need to understand it because that is something which is also will add to the depth of your knowledge of mathematics subject. So now my next topic is binary operations. Binary operations. Now see, when I take this topic binary operation, I'd like to tell you that the operations are defined over a given set. So there will be set like you have this 4 binary operation of addition, multiplication, subtraction and division, which we have been studying right from your this lower classes. So therein see, we have been talking about all these addition, subtraction, etc. in real numbers, in the set of integers, in the set of natural numbers, and so on and so forth. So point is that first we, for a general operation, binary operations to say right now, there will be a set, and over that set a binary operation will be defined. And see if we, then we will see that if we take any two elements of that set, and when we are combining them through that binary operation, and if the resultant is also turning out to be to that set, then we will say that the binary operation is well defined. Otherwise, see, earlier see in your book, NCERT book, they say they have taken like this. Otherwise, see, in certain authors, they had been defining like this, that you take any two element of the set and you combine them through that given operation, and the resultant should also be only known to you. See, the necessity that that resultant should belong to the set itself, that basically was a closure property. See, if that was the case, because the resultant could have been belonging to the set and could have been outside the set. If it was within the set, then we used to say that the given binary operation satisfies the closure property. But here in your NCERT book, they have taken it like this. The definition of this binary operation they have taken like this. They are purposely saying that see, a set is if a set is given, if some set A is given, then the binary operation is a function from A cross A to A. From A cross A to A, that is, the resultant should belong to the set itself. So let us subscribe by what NCERT definition has been given, because once a thing has been taken as a standard, then of course we need to abide by it. So with this understanding, binary operation, the notation of course will be say something like some star or something, you can use it off. So I am here defining. So basically in binary operation, what we do take any two, there will be a set, and we will take any two elements, we will combine them through that binary operation, and then that resultant will also be belonging to your given set. So a binary operation here, please write down, a binary operation, definition let us look in. A binary operation, symbolically written like this, a star is a function, from where to where? A binary operation on a set A, See, this is important. On a set A is a function such that, now see, function f followed by two lines, A cross A to A. So this is the definition. See, here in function we used to write f, here we are making this is star. This is representing our binary operation. So symbolically we will be writing this thing. So it is a function from A cross A to A. What it means to say that you take any two elements of the set, and through that binary operation, see, if the resultant is again, you are combining them, and see, you are obtaining a new element. And that if that element belongs to the same set, then you say a binary operation is well defined over the given set. Now, another this symbol which we would be using here, it could be that if we are combining two elements through the given binary operation, suppose A is our set, and AB we are combining through our binary operation, then this is written as A binary operation B. A binary operation B. So this is the symbolic way of writing of combination. So this is symbolic way of writing, A operation B, A operation B. Either this way or this way, both ways. Now we have to study certain properties here. We have to study certain properties here as far as binary operations are concerned. Let us see what those properties are. So first property here which we have to study is the commutative property. And mind it that when we are talking about these properties, that is commutative property, associative property, identity element, then do bear in mind that we will have a set, and over that set a binary operation will be well defined in it. So now see commutative property. So here what we need to tell you is that let A be a set. Now see, as I said, let A be a set, and a binary operation defined in it. defined over it. Okay. Then we say commutative property holds good, property holds if A operation B is equal to B operation A for every AB belonging to A. For every, see, you take any two elements of your set A. Either you combine A operation B or you form B operation A. Then the resultant should be same. For example, if in real numbers, if you take addition at the binary operation and say it is natural number or real number, then A plus B is equal to B plus A. It will hold good. But if you take subtraction, then it won't hold good. If your binary operation is the ordinary subtraction, that it won't hold good. Similarly, for multiplication, it will hold good. For division, it won't. So this is one thing. So do depending upon your set and do depending upon your binary operation, one can find it out whether the commutative property will hold good on the set with the given binary operation or not. And the second property is associative property. In associative property, what we need to do is that we will, now see here 3 elements will be taken, but remember that in binary operation only 2 elements at a time are to be taken. Then only, it is not that 3 elements simultaneously you can take it. Only at a time you have to take 2 elements. So we say, to again see, let A be a set and a binary operation defined over it. Then we say, associative property holds. Associative property holds on A under given binary operation, under given binary operation, if what should happen? A operation B operation C should be equal to A operation B operation C. See, bracket is immediate. For every A, B, C belonging to your set A. If this is happening, means you take any 2 elements first. So that and then whatever you get, with that you operate with the third element, and the resultant, if it is equal in both the sides. Here see what the difference is between the left side, right side. Here you are taking A and combining A and B first. And then whatever the resultant comes up, that is being combined with the C. Here you are combining B and C first, and whatever the resultant is coming, that is being combined with A. So if in both the cases, if the result is same, then you say that associative property holds good. Associative property holds good. That is, this placing of this bracket is immaterial, if at all associative property holds good. And so this is what means by associative property. And now here see, we will talk about existence of identity element. So what it has to say, please see. Existence of identity element. And this identity element will be denoted by E, small e. Now see, all these properties, as I have been repeatedly saying, that they make sense only when there is a set, and over that set a binary operation is defined. So let A be a set. Let A be a set with say binary operation defined over it. With binary operation defined over it. Then we say an identity element exists. Then we say that identity identity element exists if there exists an element E belonging to A such that A of A binary operation E is equal to E binary operation A is equal to A. For every A belonging to A, then E is said to be the identity element. Then E is said to be the identity element. For example, you take the real numbers and therein, and let the operation be say addition. Then see 0 is the natural identity element therein, because you add 0 to any number either from the left side or from the right side, you will get the same number. Likewise, if you take your set to be real, that of real number, and if you take multiplication to be the operation, then 1 is the identity element. Then 1 is the identity element. But if you take division operation, then of course see what do you feel? Will you get this identity element? That you need to ponder, because that will give you a better insight. So this is what identity element is all about. Now there is a last property left out, and that property is invertibility of an element. Invertibility of an element. Invertibility of an element. Now, so fourth property, please do write it. It is regarding invertibility of an element. Now here see, let again A be a set with binary operation defined over it. Let E be the identity, let E be the identity element of A under the given binary operation, under the given binary operation. Then we say that A naught element of A is invertible. We have taken some element of your capital A set, and we will say that A naught is invertible if there exists B naught element of A such that A naught operation B naught is equal to B naught operation A naught, and this should produce the identity. If this is producing the identity element, then you say that A naught is invertible element of the set A. So invertibility will be for individual elements. See, you take an element, and if you are in a position to find another element in the set, so that A naught operation B naught is equal to B naught operation A naught, and in both the case situation you get identity element as the resultant, then you say that the given element of the domain of the set is invertible. So this is all about these four properties. Now one more thing here I would like to tell you, that there is this operation table which we call it. So this operation table at times is useful when the number of elements in the set are small, are less, are finite and too less. Because if there are say 5 or 6, 7 or at the best n, then what we need to do is we need to draw a table having n rows and n columns, like 1, 2, 3, 4, 5 and 6. And then again 6 columns here. 1, 2, 3, 4, and 5, 6. And then what we need to do is we need to just push them further here, elongate it, and we will write the elements here. All elements of the set. Suppose A has got 6 elements. Then what we do is we suppose the elements are A1, A2, A3, A4, A5, A6. Then we will write them here A1, A2, A3, A4, A5, A6. And this will be your operation. This will be your given binary operation. And here see the ith element. For example, the second row and fourth column. This will give you A2 operation, A4. So whatever the resultant is, that you would be writing here. A2 operation, A4. So 2 fourth element will give you A2 operation, A4. Likewise, ith element here. This ith column, this cell will give you AI operation AZ. AI varying from 1 to 6 and J varying from 1 to 6. So this is how this operation table is obtained. So this is all about it. Questions are easy. You can try it, and we will give you the solution for that if in case you encounter any difficulty. Thank you.